Alright, hello everyone. In the live lecture last Wednesday, we studied how to describe a dynamic game. More precisely, we studied how to represent a dynamic situation in an extensive form. Such an extensive form representation can be done by drawing a game tree like this. And the game tree consists of several decision nodes and branches. And we also studied how to translate into normal form representation. And in the normal form representation, we needed to specify the number of players and the list of strategies and the payoff from each possible outcome. All right. But when we describe a dynamic situation in a normal form representation, so every game can be put into normal form game or into extensive form representation. But when you represent a dynamic situation in a normal form, we should be careful about the strategy. Especially when players have multiple information sets. There will be subtle difference between possible actions and possible strategies. So we should be careful about the when we identify the player strategies. Okay? So remember, a strategy is defined as a contingent plan. So it has to specify what that player intends to do at every information set. Anyway, so we studied the difference between possible actions and possible strategies in extensive form game, especially when players have multiple information sets. Okay. And then we also studied how to represent randomization in extensive form games. So, we have two possible strategies for randomization: mixed strategies, and those are defined in the same way. So it can be put as a probability distribution over possible strategies. And in extensive form representation, we have a more efficient way to express such a randomization. There's a behavior strategy. Yeah? And we study the outcome equivalence between these two in games of perfect recall. Yeah? So that is what we studied in the live lecture last Wednesday. And in this video, what I'm going to do, we are going to study how to make a prediction in a dynamic game. Okay? So to illustrate the basic idea, if we go back to this entry deterrence game between two players, so there's a one entrant and one incumbent. Okay? So in this game, entrant moves first, choosing between staying out and entering the market. If the entrant decides to enter, okay, so to choose in, now incumbent has a chance to move, choosing between fight and accommodate. Okay? So from this representation, we can see that each player has just one information set, because when entrant decides to stay out, there's no chance for incumbent to move. The game comes to an end right away. So in that case, if we translate into normal form, each player has two possible actions equivalently, two possible strategies. There is no difference between action space and strategy space. So after converting this into normal form, we are going to obtain 2x2 matrix like this. Alright, so how to make a prediction in a dynamic situation? Because now we know how to place a given situation in a normal form. Okay? And in such a normal form game, we didn't know how to make a prediction. In the previous part, we studied three solution concepts: ISD, rationalizability, and Nash equilibrium. So applying one of those concepts, so after converting into normal form game, we can make a prediction. Okay? So to illustrate this, if we consider this 2x2, if we first apply ISD, because this game deals with a two-player game. In such a game, ISD and rationalizability are the same prediction, right? So if we first apply the ISD, you can easily verify that ISD does not help in this game, because there are no strategies strictly dominated. So we can't make a sharp prediction using IST. So let me adopt Nash equilibrium to make a prediction. So it turns out that because if we examine, so if we adopt Nash equilibrium to examine each player's best response, for the entrant, staying out is the best response to fight, and choosing in is the best response to accommodate. And conversely, for the incumbent, in case of out, two strategies yield the same payoff. So both can be counted as best responses for the incumbent, and in case of in, accommodating is the unique best response. So we can easily identify two pure strategy Nash equilibrium from these best responses. In the first, incumbent, so the entrant chooses out and incumbent chooses to fight. In the second, entrant chooses in and incumbent responds by accommodating that entry. And additionally, we have a set of mixed strategy Nash equilibrium where the second player, the incumbent, put weight on fight more than 2/5. As long as this weight is more than 2/5, entrant responds by choosing out. Alright, so this is one way of making prediction in dynamic situation. So once again, we first convert the given dynamic situation into a normal form game after identifying each player's strategy. And by adopting Nash equilibrium or ISD, we can make a prediction about players' behavior, right? But we want to so we first demonstrate that prediction based on Nash equilibrium has some problems. So it has some shortcomings. So to illustrate them, if we think about the first Nash equilibrium, the second Nash equilibrium is fine, but the first Nash equilibrium has some drawback, has some problems. So to illustrate what problem that Nash equilibrium has, if we think about the player's behavior in this Nash equilibrium, in this Nash equilibrium, from E stays out, and from I chooses fight. So in order to see rationale behind playing O, so why entrant chooses to stay out to F? Because under Nash equilibrium, so in the Nash equilibrium, each player has a correct conjecture about the opponent's behavior. So entrant knows that if he enters, incumbent responds by fighting. In such a case, the payoff is just a -3. But by staying out, he can promise himself a payoff of 0. So that is way better than this situation. So staying out is indeed the best response for the entrant. For the incumbent, as long as the entrant decides to stay out, the game comes to an end with this payoff factor. Meaning that no matter what strategy adopted from I at this information set, it does not affect incumbent's payoff. Incumbent's payoff is fixed by 2. So every strategy at this information set, as long as entrant stays out, is rationalizable in the sense that it doesn't maximize from I's expected payoff. So when entrant plays O, playing F is indeed the best response. But this OF cannot be counted as a sensible prediction, because if we reconsider incumbent I's play at this information set, fighting gives a payoff of -1, and accommodating gives a payoff of 1 to the incumbent. That means if the play reaches this information set, then incumbent I should have adopted this strategy, accommodation. In other words, if we think about the situation in this first Nash equilibrium, okay, in this Nash equilibrium, incumbent intimidates the entrant by saying that if you choose in, I'm gonna fight with you, so then your payoff is just a -3. It's way better to stay out. Okay, so incumbent attempts to threaten the entrant like this, right? So if that threat works, so if entrant plays stay out as desired, then the payoff is realized. So 0 and 2 are realized as desired. But what if the entrant disregards that threat and decides to enter the market? Okay, so then originally incumbent I has a plan to fight. Okay, but if we observe that, so if we observe the entrant enter the market, then now he is willing to advise. So he is willing to revise his strategy from fight to accommodate. Now, because accommodate is a unique best response for the incumbent. Okay, so this O and F is a Nash equilibrium because O is a best response to F and F is a best response to O. So these two are mutual best responses. But this equilibrium is based on non-credible threat or empty threat, in the sense that if firm indeed chooses I, an incumbent is willing to change his plan to F to A. Yeah? So in other words, F is a never best response at this information set. Yeah? And O and F can be supported as a Nash equilibrium because whenever entrant stays out, playing never best response at this set can be rationalizable. But this Nash equilibrium is based on empty threat, requiring incumbent play a non-best response at this unreached information set. Yeah. So we formally call such a play, playing non-best response at the unreached information set empty threat, or non-credible threat. So the I's play, playing F is empty threat in the sense that once the play reaches incumbent's information set, then incumbent is willing to change his strategy because he never wants to choose to fight. Alright, so that is one major problem with the Nash equilibrium. When we make a prediction based on Nash equilibrium in a dynamic situation, we can't eliminate such a play based on empty threat. It gives us 3 possible predictions, but except the second, the first and third based on empty threat. Right? And this is why we propose a new solution concept. And this is why many game theorists doubt that Nash equilibrium is the appropriate solution concept in extensive games. Because it doesn't address the problem of credibility of commitment. Although incumbent I has a plan to choose F, but he cannot commit to this plan if he observes from E enter the market. Alright, so to better understand this empty threat, let me consider one more example, the so-called Stackelberg duopoly. Right? So this game is very similar to Chrono duopoly in that there are 2 players and 2 firms compete with each other by choosing quantities. Okay? But in this Stackelberg duopoly, there is a leader and there is a follower. Okay? So usually we put firm 1 as a leader. Yeah? So he chooses Q1, quantity first. And observing this quantity, firm 2 moves next by choosing Q2. Okay? But they compete each other in the same market, meaning that 2 firms produce the identical goods. Yeah? So after choosing Q1 and Q2 by both firms, the market price, the unit price of the good is determined by this linear equation. Okay? And to simplify our discussion, we are going to assume that there is a no cost for production. Then, in this case, if we represent this game in an extensive form, and there is a firm 1. So firm 1 moves first by choosing Q1. Okay. And observing this, firm 2 moves next by choosing Q2. Okay. And the payoff, because firm 1's payoff is going to be P times Q1, because we assume there is a no cost. Okay. So the revenue will be identical to the profit. So instead of P, we can substitute the market demand function to express the payoff in terms of Q1 and Q2. All right, and then firm 2's profit is P times Q2. So market demand times Q2. Okay, so in this dynamic game, so firm 1 chooses first and firm 2 chooses next. We consider the following strategy profile. Firm 1 produces 2 units, and firm 2 responds by producing this amount of units. Yeah? Because now, if we think about firm 2 strategy, there are infinitely many information sets for player 2. Because for each choice by firm 1 induces one information set. Okay? So when we describe firm 2 strategy, we have to specify what the firm, which quantity the firm 2 is willing to produce. Okay, I mean at each possible choice of Q1 by firm 1. Okay, so the firm 2 strategy is not a single quantity, but instead some function of Q1. Okay, so this strategy is given by piecewise function. So if firm 2 observes firm 1 produce 2 units, firm 2 responds by producing 5 units. But if he observes the other quantities, he produces this amount of quantity, this amount of output. All right, and let me first demonstrate this choice. So producing 5 units in response to 2 units is the best response for firm 2. Okay, that is easy because if Q1 is given by 2, then firm 2's profit function becomes 10 minus Q2 times Q2 when Q1 is 2. Okay, so the profit maximizing quantity is going to be so it is driven from the first of the condition. So FOC is going to be 10 minus 2Q2, and we set it equal to 0. And from that, we can easily find, profit maximizing quantity is indeed 5 units. It's to produce 5 units. Yeah. So this is a best response for firm 2. But what about the other quantities? What if firm 2 observes the other quantities chosen by firm 1? In this strategy profile, we require firm 2 produce this amount of units, right? But if we compute the firm 2's best response, in case of general Q1, now we take this as firm 2's payoff function, and if we compute the first of the condition, that is going to be 12 minus Q1 minus 2Q2, set it equal to 0. So firm 2's profit maximizing quantity is going to be not 12 minus Q1, but is half. So 12 minus Q1 divided by 2. Okay, and now think about firm 1's behavior. If firm 2 responds with this strategy, what is the best response for firm 1? Firm 1's payoff, if he produces 2 units, as promised, then his payoff is going to be 12 minus 2, and from 1 nose down, from 2 responds with 5 units. 12 minus 2 minus 5, so the market price becomes 7, and we multiply by 5 units. So 5 times 5, Oh, so Q1 is given by 2 instead of 5. So 5 times 10. So 5 times 2, that is 10. So the profit amounts to $10. But if from 1 produces the other quantities, under this strategy profile, from 2 responds with this quantity. But with this quantity, observe that, the market price comes down to 0. Okay? So this can be understood as an empty threat. If from 2 observes the other quantity, he threatens the from 1 by saying, if you choose other quantity, I'm going to reduce the market price down to 0. Yeah? In such a case, you and I both make a 0 profit. Yeah? So the from 1's profit for other quantities will be 0. But if we think about the rational behavior using Nash equilibrium, using 2 units is indeed the best response to this strategy profile. Yeah? But once again, so this strategy profile is a Nash equilibrium because choosing 2 units is the best response to this one, and to this one, this strategy is the best response because the other information sets are never reached. Yeah? So it's enough to check the rationality about these 5 units, and we already checked this is a rational behavior when there's a profit maximizing quantity for firm 2. Yeah? So given strategy profile is a Nash equilibrium, but we can see that firm 2 strategy is a non-credible threat. For other quantities, firm 2 will has to respond with its half. All right. So now our objective is so what kind of predictions we have to provide in a dynamic situation. If we adopt a Nash equilibrium, it gives us some play based on empty threat. All right, and we treat them as a not a good prediction. So not a sensible prediction. All right, so now we so from the 2 previous examples, what we can learn is that because Nash equilibrium requires Bayesian rationality and correct conjecture about the opponent's behavior. But with rationality alone, we can't eliminate the play based on empty threat. Okay? So the previous examples indicate that we have to assume more than rationality itself in order to eliminate the player's behavior based on empty threats. Okay? So that brings us the idea of sequential rationality. Sequential rationality. And this principle requires that every player ought to demonstrate rationality whenever they make a decision. Okay, more precisely, a player's strategy should maximize his expected payoff at every information set, whether that information set is reached or not. So, going back to the previous example, this simple game, fighting is a rational behavior as long as entrant decides to stay out. It does not affect incumbent's payoff. Okay? So it can be regarded as a rational behavior, but it cannot be regarded as a sequential rational behavior because the principle of sequential rationality requires, incumbent play accommodate, although this information is never reached. Okay? So now we are going to look for players' behavior based on sequential rationality. All right. The basic idea is once again, we would like to eliminate plays based on empty threat. Okay. But with rationality alone, we can't eliminate such a play. So we have to assume a little bit more than rationality. A little bit more strong assumption on players' behavior. That is a sequential rationality. Yeah. So it requires whether that information reached or not. We require each player choose best response. Okay. And the way to identify such a strategy is twofold. Okay. The first method is the backward induction. So I think you guys have seen this kind of procedure before, but let me illustrate this with one simple example. That shows up in the next slide. So this game describes a game between 3 players. Player 1 first makes a decision between L and R. In case of L, player 3 moves next. In case of R, player 2 moves next. Okay? And after deciding between A and B, player 3 moves next. In this situation. And the backward induction procedure goes as follows. We first identify a decision node that is followed by terminal nodes. Okay, so for these 2 terminal nodes, its predecessor. Okay, the decision node is followed by these 2. That is this node, at which player 3 makes a decision between L and R. Okay? And in the second step, we'll specify the action that leads the highest payoff to that player. Okay, so here, at this node, player 3 makes a decision, and we specify which action leads the highest payoff. In other words, which one is the best response for player 3. Okay? Between L and R, L gives a payoff of 1 to player 3, but R gives payoff of 6. So clearly, R is the best response. Okay? So we specify the player 3's best response at this node. Okay? Similarly, at this node, we specify player 3's best response. That is also action R. And at this node, now action L is the best response. Okay? And we continue to this job until we reach the initial node. Okay? Now we compare player 2's payoff from A and B. If player 2 chooses action A, now player 2 anticipates that player 3 chooses R at this node. Okay? So payoff from A is going to be, payoff from A to player 2 is going to be 4. Okay? But payoff from R is just a -1. So playing action A is the best response for player 2 at this node. Okay? And we have to take one more step to reach the initial node. So now we compare the player 1's payoff from L and R. If he chooses action L, payoff is -1. And action R, then player 2 chooses A, and player 3 chooses R. So anticipating this behavior, the payoff from R to player 1 is going to be 5. Okay? So for player 1, choosing action R is going to be best response. Okay, so we repeat this procedure until the game is reduced to the initial node, like this. Yeah, and then we say a strategy profile that survives this procedure is called backward induction. So we say that any strategy profile that can be obtained by this process is said to survive the backward induction procedure. Yeah. So the strategy profile survives the backward induction procedure in this example is going to be, for player 1, is to choose action R. And notice that for player 1, he has just one information set. Yeah. So the action space is identical to strategy space, and so does player 2. His action space is identical to strategy space. Okay? And in this path, okay, action A survives. Action B, so that is eliminated. Okay? So we have strategy A for player 2, and for player 3, he has several separate information sets. Okay? And remember, a strategy for player 3 has to specify what he intends to do at every information set. Okay, so those strategies surviving this procedure is action R at the first information set, and action R at the second, and action L at the last. R, R, and L. Okay. Alright, so it turns out that this strategy profile survives the backward induction procedure. Okay. So, if we compare this backward induction with ISD, in ISD, I mean in normal form games, ISD, is based on the idea of eliminating the never best responses for each player. Okay, so we can see that backward induction has a similar flavor to ISD. So in extensive run game, using backward induction, we eliminate non-best response for each player like this. Okay? And then you can easily see that the strategy profile surviving backward induction procedure is sequentially rational. Because backward induction requires player 3. This information set is never reached. Nevertheless, we require that. So we require player 3 choose action R. Okay? So any place at this information set under this strategy profile is rationalizable because it doesn't affect player 3's payoff. So under Nash equilibrium, any place can be survived, but under sequential rationality, only action R is rationalizable. Okay? And so is at this information set. This information set is never reached, right? Because play will reach this information set and this one. But nevertheless, sequential rationality or backward induction requires player 3 use action L. Okay? As such a unreached information set. Alright, so whenever we adopt this backward induction, we can identify unique path from the initial node to one final node, like this. Yeah? In every extensive run game with no payoff ties. Whenever we have a tie in payoffs, like if we change this -1, so the player 1's payoff at this strategy profile, say to 5. Okay, and now we apply backward induction procedure. We obtain the same result up to this point. And now for player 1, action L and action R yield the same payoff. Okay, so this one will survive the backward induction procedure as well as this one. L, A, R, R, L also survives the backward induction procedure. So we have multiple paths in case of ties, but in case of no ties, we have a unique path from the backward induction procedure. So that is one way of identifying sequential rational behavior. I mean, so our prediction after eliminating plays based on empty threat. Yeah. Now what we are going to do, we are going to make a link. So we are going to create a link to one equilibrium concept. So we are going to develop one corresponding equilibrium concept to backward induction procedure. Okay, I mean so our prediction based on fulfilling the principle of sequential rationality. Okay, that is the so-called subgame perfect equilibrium. Okay, but in order to describe this equilibrium, we have to start with a subgame. Yeah, because this equilibrium notion is based on so the concept of a subgame, right? So a subgame is defined as a portion of the entire game, okay, that starts from one decision node X in that extensive run game, okay, and includes all subsequent nodes. All right, so if we go back to this example, starting from, so subgame is some portion of the entire game. Okay, so if we take this portion from the entire game, you know what? This game starts from player 3's decision node, and it includes every subsequent nodes. I mean these two terminal nodes. Okay? So it can be taken as a subgame. This can be taken as another subgame. It starts from these decision nodes, player 3's decision node, and includes all subsequent nodes. I mean, including these two terminal nodes. Okay? And then subgame starting from player 2's decision nodes. Okay? So from this, we have to include all subsequent nodes. So have to include this 2 like this. So it can be regarded as another subgame. Okay, and starting from this decision node, this one is another subgame too. All right, and starting from this one, now we have to include everything, every piece. So the entire game also can be regarded as a subgame. Okay, so the definition of the subgame is easy to understand. It can be thought of as a subset or portion of the entire game. Starts from one decision node and includes all subsequent nodes. Yeah, but one thing we should be careful about this subgame, especially the information set must be inherited from the original game. Okay, so this point can be illustrated by this example. Suppose that we have this extensive from game. Player 1 first chooses between T and B, and player 2 cannot observe player 1's behavior. So player 2 cannot distinguish these two decision nodes. So they are put in the same information set. Okay? So in that situation, player 2 chooses between L and R. Okay? And you may think of one portion of this game, say this one, starting from node Y. Or starting from node X. Okay? And we may include this portion as a proper subgame of this extensive form, right? But if we take this one, yeah, and then put it right here, all right? And if we take a look at this subgame, now it seems like player 2, although in the original game 2 cannot distinguish X and Y. In this subgame, it seems like player 2 now can distinguish X and Y. Right? So it should not be counted as a subgame because in the original game, we have just we have just one information set for player 2. Okay? But if we separate these two, treating each as a proper subgame, then we treat so then we assume that player 2 can distinguish X and Y. It violates this condition. Information set must be inherited from the original game. Okay, so that means when we consider subgame, so whether a given portion is a subgame or not, we should not cut off any information set of the original game. Okay? So the only possible subgame for this extensive form is the entire game. Starting from this node, includes every following nodes. That's going to be entire game. Okay? So let me illustrate. So let me show you one more example in the next slide. So in this game, if you think about how many subgames exist, so from this node Y, yeah, the portion, this portion, can be taken as a subgame. Okay? But if we want to start from X, it should include all following nodes, these 4 nodes, right? So like this one. So starting from node X, now we include every subsequent nodes like this. Yeah. So this is one portion of the entire game. But if we take this one, we couldn't help cutting off this information set. Alright, so if we cut off this one, now it seems like player 3 can distinguish Z and W, but in the original game, he cannot distinguish. So although this is a portion of the entire game, it is not counted as a subgame. And for the same reason, this is not counted as a subgame. This is either. When we take up this portion, we have to cut off this information set. Right? So the other possible subgame is the entire game. So this game has just the 2 subgames. The entire game starting from the initial node, and one proper subgame starting from node Y. This one. So this is a one-purpose subgame, and the entire game is the other possible subgame. And so there are just the two. All right. And now I'm going to define subgame perfect equilibrium based on this notion. But to illustrate this, we have to define restriction of strategy to possible subgame. Okay. So let me define sigma I given x. So sigma I given x as the player I's strategy. So restriction of player I's strategy to subgame gamma x. Okay. To understand this notion, so if we think about the following strategy for player 1, U and E. Okay. So at this first information set, player 1 attempts to choose U under this strategy, and at the second he attempts to choose E. Okay. And so if I call this S1, player 1 strategy in this extensive from game, is restriction to say Y. Yeah. So it's restriction to this subgame. Okay. In this subgame, under this strategy, he's willing to choose action E. Okay. So that is going to be action E. Yeah. Okay. All right. Then we are ready to define subgame perfect equilibrium. So let gamma denote the n-player extensive from game, and gamma sum x denote its possible subgame, starting from node x. Okay. And we define subgame perfect equilibrium as a strategy profile. So we have to specify each player's strategy in that extensive from game, and to be a subgame perfect equilibrium, it has to induce Nash equilibrium in every subgame gamma sub x, meaning that if we focus on subgame starting from node x, its restriction for player I, so the restriction of player I strategy to that subgame should be player I's best response to the other restrictions. Okay. So in other words, SPE, subgame perfect equilibrium, requires Nash equilibrium play in every possible subgame. Okay. SPE can be thought of as Nash equilibrium play in every subgame. All right, because think about this, this condition. Each player plays a best response to the other player's equilibrium strategy. That is exactly complies with the definition of Nash equilibrium. Okay, but the difference between Nash equilibrium and SPE, now SPE requires this equilibrium play in every possible subgame. All right, so let me mention two remarks on this definition, this equilibrium notion. Okay, first, any extensive from game has at least one subgame. I mean, even for this extensive from game, it has a subgame, right? The entire game, right? So every extensive from game has an entire game as a possible subgame, and remember, all subgame perfect equilibrium requires Nash equilibrium play in every subgame. So that condition includes the equilibrium play in the entire game, right? But if we have several, so if we consider this example, the Nash equilibrium play requires rational behavior in the entire game only. Yeah? But SPE requires two things: rational behavior in the entire game plus rational behavior in this subgame. All right, so whenever a game has multiple subgames, we can see that subgame perfect equilibrium is a subset of a Nash equilibrium. Okay, I mean SPE, this set, is going to be a subset of a Nash equilibrium. Okay, as a Nash equilibrium requires just one condition: rational behavior in the entire game. But subgame perfect equilibrium requires Nash equilibrium play in every subgame. Right? So we can easily see that SPE requires more conditions about players' behavior. So as a result, SPE becomes a subset of Nash equilibrium. Okay? So in this sense, we say that SPE is a refinement of Nash equilibrium. Some plays will be refined. Okay? So for example, this guy, this one, that will be refined by the subgame perfect equilibrium. So it includes, it specifies rational behavior in the entire game. Okay? But it does not require rational behavior in some proper subgame. So that is ruled out by the SPE. Okay? So SPE is a refinement of Nash equilibrium. And the second bullet point says, if there is a no proper subgame, okay? I mean, if a possible subgame is the entire game only, then there is a no difference in this definition of SPE with the definition of Nash equilibrium. I mean, SPE and Nash equilibrium give us the same predictions about players' behavior. Yeah? For example, if we compute SPE in this game has just the entire game as the unique subgame. All right. So, imposing Nash equilibrium in every possible subgame is totally equivalent to imposing Nash equilibrium play in the entire game. Right. So SPE and Nash equilibrium will yield the same prediction as long as the game has the entire game as the unique subgame. Right. All right. So let me illustrate how to compute subgame perfect equilibrium using this example. All right. In this example, we have two subgames. So one is the entire game, the trivial one, and the other is a proper subgame starting from player 1's decision node. Okay? I mean, this one can be regarded as a one proper subgame. Right? We did not cut off this information set, and this portion includes every subsequent nodes. All right. So SPE requires rational behavior in the entire game. So if we represent the entire game into normal form, okay? So SPE requires Nash equilibrium play in this game at the same time. So additionally, it requires Nash equilibrium play in this subgame. So this is a normal form representation of this subgame. Okay? In this subgame, player 1's strategy is just A and B. Because he has just one information set in this subgame, in this proper subgame. Right? And so does player 2. He has just one information set. Okay? So his strategy space is going to be action space, X and Y. So its normal form representation is going to be 2 by 2. All right. So in this subgame, if we think about Nash equilibrium play, player 1's best response is to choose A to X and choose Y. Is to choose B to Y. Okay? And for player 2, to A. X and Y are both best responses, but to B, X is a unique best response. Right? So, A comma X, we can see that A comma X is the unique pure strategy Nash equilibrium. I guess there will be several set of mixed strategy Nash equilibrium. Let me leave that as an exercise. But if we focus on pure strategy Nash equilibrium, A comma X is the unique Nash equilibrium. All right, and So remember, SPE requires two things: Nash equilibrium in this subgame and in the entire subgame. Okay. So now we consider Nash equilibrium play in the entire game. But in the entire game, now player 1 strategy now is 4 tuple. So 4 tuple vector. Because now player 1 in the entire game has 2 information sets. Yeah. So one strategist has to specify what player wants to do at this one or at this one. Yeah? So we have a total of 4. Okay. So in this entire game, we have a 3 pure strategy Nash equilibria: UANX and DANY, okay, and DBY. Okay. I think this is a routine task. So to check whether these are Nash equilibria is a routine task. So let me leave it as an exercise. So now what is a subgame perfect? So let me illustrate what is a subgame perfect equilibrium in this extensive from game. Alright, so you know what? We have 3 candidates for subgame perfect equilibrium. But remember, it's restriction to this subgame. Yeah. So the restriction to this strategy profile to this subgame is going to be a comma x. That is consistent with the Nash equilibrium in this subgame. So this one is going to be SPE. Yeah. But what about this one? It's restriction to this subgame. Okay. Now player 1 chooses action A, strategy A, and player 2 chooses action Y instead of X. So because we have different predictions about player 2's behavior, right? Its restriction is no longer Nash equilibrium in this subgame, right? So that's why we can eliminate this one. And for DBY, its restriction to subgame is going to be BNY. Okay? So that is totally different from this Nash equilibrium play. So we can eliminate that. We can eliminate this one too. All right. So UN and X is going to be unique subgame perfect equilibrium in this extensive from game. Yeah. Now let me show you one more example using the previous Stockerberg duopoly game. This was the extensive form representation of this Stockerberg duopoly, and notice that for each choice of a Q1 we have a corresponding subgame, right? So we have infinitely many subgames here. I mean, for each choice of a Q1, identifies player 2's possible information set. At the same time, it defines possible subgame for player 2. Okay, but for each generic subgame, in this subgame, it is only player 2 who makes a decision, right? So the Nash equilibrium in every possible subgame is going to be so if from 2 observes Q1, the profit maximizing output was the so Q2 star was 12 minus Q1 divided by 2. Okay, so remember SPE requires Nash equilibrium play in every subgame. Okay, so now we are going to consider Nash equilibrium play in the entire game. Okay? But we know that if we restrict to this subgame, player 2's equilibrium strategy, I mean SPE, should be this one. Okay? Just like the in the previous example, we know a comma x is the unique Nash equilibrium in this subgame, right? So if some strategy is a SPE, its restriction to this subgame should be a comma x. Okay? So that's another way to find SPE. We only consider intersection between these two. Yeah. So UA and X has the only intersection with this a comma x. So this is why we regard that, we take that as a SPE. Alright, so we know Q2 star is this one. Okay, this one. So now, without loss of generality, we can substitute this player 2's best response into player 1's payoff function. Yeah. Alright, so anticipating from 2's optimal best response, from 1 chooses Q1, his own quantity, so as to maximize his own profit. So after substitution, now this guy is going to be function of a Q1 only. So the from 1's best response can be easily computed from the first order condition. Yeah? So from 1 produces 6 units. So this game has a unique subgame perfect equilibrium. And when we describe equilibrium, remember that we have to specify the player's strategy profile. Yeah? And player 1 has just a one information set. Yeah? So one single number is going to be, one possible strategy. So, from 1 in SPE produces 6 units. But from 2, it has an infinitely many information sets. So although from 2 can observe from 1's choice, so in the end here going to produce, it's going to produce 3 units. 12 minus 6 divided by 2. Yeah? But that is an equilibrium outcome. Yeah? When we specify equilibrium, we have to specify player strategy profile. Yeah? So we have to specify what quantity is to be chosen by from 2 at every information set. Yeah? At every information set, in other words, at each quantity Q1 chosen by from 1, from 2 is willing to produce this quantity. Alright, so yeah, let me just mention one more thing. That is a first mover advantage. Okay, so if we compare this Stackelberg result with Krono-Nash equilibrium, okay, in Krono-Nash duopoly, we assume that both firms simultaneously move by choosing quantities. Okay, so in the same situation, in the same market demand function without production cost, Krono-Nash equilibrium is going to be this one. So each firm produces 40 units. Okay, I think this is a simple exercise. So let me leave it as an exercise. Okay, for you. So verifying these 40 units is the unique Nash equilibrium in Krono duopoly. Okay? But instead, in Stackelberg game, so if from 1 chooses first and from 2 moves next, and from 1 chooses 6 units, and from 2 follower chooses 3 units. Okay? So this is the Stackelberg SPE outcome. Okay? And if we compare these two by computing each firm's payoff, so in Krono-Nash equilibrium, because each firm chooses 40 units, so the profit, because the game is asymmetric, so it's enough to check the firm 1's profit. Firm 1's profit will be the same as firm 2's, which is going to be 12 minus 4 times quantity produced, which is 16. Okay? So Yonsei payoff in Krono duopoly for firm 1 and U2C. Firm 2's profit in Krono duopoly, both of them amount to 16. Yeah? But in Stackelberg game, now if we compute firm 1's, so the leader's profit, U on S is going to be 12 minus from 1 produces 6 units and from 2 respond with 3 units. So the market price is going to be 3 units. So the market price is going to be 3. Okay, and because from 1 produces 6 units, So his profit amounts to 18. Yeah. So comparing with the current Nash equilibrium, we can see that leader can gain a little bit more. Yeah. On the other hand, follower in Stockberg game, his profit is 3 times 3, that is 9. So compared to current Nash, follower becomes worse. So he's getting worse, leader is getting better. Okay. So we call that additional advantage of the leader. Okay, so the extra gain or extra benefit from moving first, or the first mover advantage. So in extensive from game, in games of perfect information, okay, leader has an extra gain by moving first. Okay, always. Yeah. So this is called the first mover advantage in game theory. All right. So this may sound a little bit counterintuitive because if we compare two games, in Stockberg, firm 1 chooses Q1, okay, without observing Q2. But instead of Q2, also firm 2 chooses Q2 after observing Q1. So if we think about each firm's amount of information when each firm makes a decision, firm 2 has a better information because when he makes a decision, he can observe Q1. Yeah? And in chronoduopoly, no firms have some informational advantage because both firms make a decision at the same time without observing the other firm's quantity decision, right? So if we compare these two situations, now we can see that firm 2 in the Stockberg game has some informational advantage. So he has more information. He is better informed. Okay? But such a better information would never hurt players' payoff. It turns out that if firm 2 has more information, his payoff will be, so he's getting worse from having more information. Now his payoff is just a 9 in Stockberg game. Okay, so to better understand the intuition behind this striking result, now observe that although firm 2 has additional information, when he makes a decision, he can observe Q1's, so the firm 1's decision about quantity. Okay, so 2 knows Q1, firm 2 knows Q1. Okay? But that fact is not private information. This is not the information that only firm 2 knows. Okay? I mean, in fact, that information is totally shared by firm 1. I mean, firm 1 also knows that firm 2 knows Q1. So when he makes a decision about Q1, he knows that that choice is perfectly observed by firm 2. Okay, so it looks like firm 2 has additional information in Stockberg game about firm 1's choice. That information is no longer private information. Okay, and in game theory and in economics, if for information to have some value, okay, so for information to be valuable, it should be private information. It should be the only, so it should be the only player. So it should be that player who only knows about that information. Okay, otherwise, it has no values. So knowing Q1 is not a private information to firm 2. It is totally shared by firm 1. So the gain from additional information, totally disappears. Okay, totally disappears. Instead, now firm 1 has a commitment power by moving first. By producing, so not just by planning, so announcing to so announcing he has such a plan to produce 60 units. By implementing such an action, directly, and showing that to firm 2. So he indeed produced 60 units. So he has a commit. So he has a full commitment power. Okay, so by moving first, firm 1 can make a commitment to the other firm. Okay? So can make a commitment to one possible action by moving first. and such a commitment power brings the from 1, I mean the Stockberg leader, some additional gain. Yeah? So that's the source of first mover advantage, and this is also why follower gets worse in the Stockberg game. Yeah? All right, and let me finish with this equivalence theorem. So that is a summary of the so that is a main theorem in this part, and that is also a summary of the summary of our discussion. Okay, so we started with a sequential irrational behavior. Okay, the basic idea of sequential rationality is how to eliminate the play based on empty thread. Yeah, and we developed two methodologies. So two methods of finding such a behavior. The first one is a backward induction procedure. So the idea of eliminating non-best responses at each information set. Yeah, no matter whether that information set is reached or not. Okay, so it captures the basic idea of sequential rationality. And we also define subgame perfect equilibrium. It does not only require Nash equilibrium in the entire game, but also requires Nash equilibrium play in every subgame. Okay, but in extensive from game of perfect information, meaning that every successor can perfectly observe the predecessor's move when that player makes a decision. Okay? In other words, there is a no dotted line. Yeah? So this is a games of imperfect information. This is 2. Yeah? This is 2. But this is a games of perfect information. Yeah? In such a class, yeah? I mean, infinite extensive from game of perfect information. So we have a finite number of players, and each player has a finite number of actions. Okay? And the following statements are equivalent. So one strategy profile is a subgame perfect equilibrium. Okay? If and only if that strategy profile is a sequentially rational. Okay? And if and only if that strategy profile survives the backward induction procedure. Okay? So if we find some strategy profile surviving the backward induction procedure, by this theorem, that is automatically subgame perfect. And the other way is also true. If we find a subgame perfect equilibrium, so we investigate players' rational behavior in every possible subgame, and that strategy profile, SPE, will survive the backward induction procedure. Okay? So, because the proof of this theorem is really important, because that is based on the one fundamental result in game theory, the so-called one-shot deviation principle. So we are going to discuss a little bit more about this one-shot deviation principle in the live lecture this Wednesday. Let me just mention the first bullet point, okay? Because we know that from this theorem, we know that if one strategy profile survives the backward induction procedure, it's going to be automatically subgame perfect equilibrium. Okay, but in every finite extensive run game of perfect information, if we apply the backward induction procedure, we can obtain at least one strategy profile surviving this procedure, right? So, going back to this example, no matter whether we have ties or not, if we apply backward induction procedure, we can obtain one strategy profile at least surviving this procedure, right? And by this theorem, equivalence theorem, we know that is a subgame perfect equilibrium. Yeah. So to summarize, there is at least one strategy profile surviving backward induction procedure. Okay? And by this theorem, we know that is a subgame perfect equilibrium. Okay? So that ensures existence of subgame perfect equilibrium in this extensive run game. Okay? So every gamma has SPE. So using the equivalence between 3 and 1, we know that every gamma, so every finite extensive run game of perfect information has a SPE in pure strategies. Because if we apply backward induction procedure, we obtain one strategy profile in pure strategies. Okay, and using the equivalence between 1 and 3, we know that that strategy profile is a subgame perfect equilibrium. Yeah? But that ensures the existence of SPE, not just in existence, but existence of SPE in pure strategies. Okay, so that is a much more stronger. So that's much more strong than the existence result in normal form game. You know what? In order to prove the existence of Nash equilibrium, the proof of existence is really long, and we have to adopt the some mathematical result, the so-called fixed point theorem. Okay, but in dynamic games, of perfect information, we we don't have to any longer apply such a mathematical theorem. So without the aid of such a mathematical theorem, we can simply prove the existence of SPE, and not just the existence, but existence of SPE in pure strategies. Okay, using the equivalence these two. Okay? All right. And furthermore, we know that if there is a no tie in payoffs, backward induction procedure gives us unique strategy profile. Okay? There will be a unique strategy profile surviving that procedure. Okay? And by equivalence between 1 and 3, now we can say that, we can also say about the uniqueness. So that is a unique subgame perfect equilibrium in that game. Okay, I mean, there will be no other subgame perfect equilibrium than this one, surviving the backward induction procedure. Okay, so if 3 leads to a unique strategy profile, so there is a one strategy profile surviving this backward induction procedure, then that strategy profile constitutes a unique SPE. Okay? So I'm going to talk a little bit about. So I'm going to talk a little bit more about this equivalence in the live lecture, because this is a key result. So central result about the second class games. I mean, dynamic games of dynamic games with complete information. Okay. All right. So let me finish with this example. So if we apply that equivalence theorem to this example, we have a several Nash equilibria in this normal form game, right? So we have several predictions about players' behavior on the basis of a Nash equilibrium. Yeah? But if we apply the backward induction, because this is a game of perfect information, there is a no dashed line. So applying the backward induction, so to this node, where incumbent makes a decision, so incumbent is given by player 2. Okay, the accommodating is a best response, unique best response. And now from each decision between out and in gives payoff of 2, out gives a payoff of 0. So in is going to be unique best response. So we have just a unique path. We obtain the unique path surviving the backward induction procedure. Yeah? And by the equivalence theorem, now we can say a little bit more. I and A, so that strategy profile is sequentially rational, and it is the unique subgame perfect equilibrium. Yeah? And remember that the game has the several pure strategy Nash equilibria, I and A, and O and I think this is a typo. It should be F. It should be F. Okay? And the set of mixed residential equilibria. Alright? So our conclusion is the main takeaway of equivalence theorem is requiring credibility of commitments. So requiring each player choose strategy, credible strategy. Okay? Credible strategy. So credibility of commitments drastically refines the set of predictions. So if we narrow down to behavior so sequential irrational behavior, we only obtain the single prediction. That is it. Entrant chooses I, and incumbent chooses to accommodate. Okay? Alright, so this is a 75 lecture video, but in this video I illustrated the basic idea of how to make a prediction in dynamic games with complete information using backward induction and using subgame perfect equilibrium. So in the live lecture Wednesday, what we are going to do, we are going to see the several applications of subgame perfect equilibrium. Okay, so hope you enjoyed this video. Then I'll see you next Wednesday.